So let's discuss some solutions to this wave equation. So let's look at solutions. So let's take what I would call an ansatz, or a solution, a proposed solution. So because it's a wave equation, I'm claiming it's a wave equation, it should admit some nice sine wave or something as a solution. So let's take y to be our proposed solution. So this is sine of kx minus omega t, and k and omega are constants because sine is it's a power series, right? The sine function. So its argument has to be something that is dimensionless. So the angle, this is angle, and angle expressed in pi radians, and that is a dimensionless quantity. Whereas x and t are not dimensionless, so omega has to have dimension of 1 over time, k must have dimension of 1 over length. All right, let's see if this can solve that wave equation. So if we work out what the second derivative with respect to x is, then what we get is that sine, if I take the derivative of sine, I get a cosine, and the derivative of cosine gives me a minus sine, and then two derivatives gives me k squared, and therefore I get minus a k squared sine of kx minus omega t. On the other hand, if I look at the second derivative with respect to time, then I get minus a omega squared sine of kx minus omega t. And so as long as we have k squared is equal to omega squared by v squared, then which of course implies that v is omega by k, then we know that this thing is going to be a solution to this equation. So that's very good. So we have determined that there are wave solutions to our wave equation. So of course this is a wave which is traveling to the right, and this is because of this minus sign. And we can ask, can we have a wave solution which is traveling to the left? And so if I had taken y to be, say, a sine of kx plus omega t, then I would have found that this is also a solution to the wave equation. Of course, we've taken sine, but we could have easily taken cosine. So we could have taken say, cosine of kx plus omega t. And the difference between this solution and the sine solution is that they differ by a phase. And so this shows that, so this is a second order differential equation. So to integrate this, we have to provide two boundary conditions in terms of time. And so these two boundary conditions are given, the integration constants are given by a and phi here. So this is a very good solution to the wave equation. So let me just make sure we are clear. This is a left moving wave, and whereas this guy was a right moving wave. Now there's something interesting that one can notice, that one can ask whether the wave equation needed to be second order. Because what if I say, okay, if I suppose that I have if I take the first derivative of, say, y, where y is given by a sine of kx minus omega t, then I have then I can get k of y. And if I take the first derivative with respect to x, I get minus omega of y. And therefore, this y equation solves this wave equation. So we could have asked, so this is also could be a wave equation, and it could be, we could say this is the solution. The problem with this wave equation is the following. If we take a wave which is traveling to the left, so which has y equal to a sine of kx plus omega t, and then we repeat these steps, then we find that this guy does not satisfy this wave equation, but it satisfies a different wave equation where instead of minus sign there's a plus sign. So, so basically, if we ask for a first order wave equation, we can only have either left moving waves or right moving waves. So having a second order wave equation here allows us to have both left moving and right moving waves. So this is an interesting observation, and something similar will come up when we are considering the Schrödinger equation. However, before we get to the Schrödinger equation, let me just talk a little bit about some generalizations of this one-dimensional wave equation. So this is my generalizations. So for example, we could be talking about the waves in a drum, in a taut surface, right? So in a taut surface, it'll be a two-dimensional system, and then we could have the displacement could be u, and then this would be given by something like this. So there should be a squared here. And one can imagine some system which is three-dimensional, and for example, sound wave, and it could have a three-dimensional version of it. And let's just write our stuff in vector notation, vector calculus notation. I'm hoping that you know what this is, otherwise please ask me. And this is going to be 1 over c squared. C is some, the speed of the wave, and this is, by the way, sometimes this equation is written in a shorthand form by introducing an operator called the D'Alembert operator, which is a box. So the D'Alembert is defined as this operator. It's a linear operator which generalizes the Laplacian. So in terms of the D'Alembert, the 3D wave equation is just, this. All right. So, so you might ask, okay, where can I get a wave of this form? So you could show that Maxwell's equation, so that from the Maxwell's equation, you can derive, such a wave equation. And that is going to be our next topic. But before we get to the deriving a wave equation from Maxwell's equation, let me just tell you that there are wave equations which are not necessarily of this form. I've told you this before, and there is a very famous wave equation. It's called the Kdv equation, and the Kdv equation is a wave equation for waves in shallow water. And you can derive it from Euler's equation, which is basically Newton's equation, but for fluids. And then the wave equation, the Kdv equation, has a form in one dimension, the du by dt plus u du by dx plus some constant called delta squared, and a third derivative of u. So one thing to notice is that this is actually a nonlinear wave equation. See, there is a term where, the derivative of u multiplies u. So this is a nonlinear wave equation. It's a very famous equation, and the solution of this is related to a law of mathematics called integrable systems. Anyway, we won't go there today. But I'll finish now here, and in a short segment after this, I'll talk about Maxwell's equation and how we can get a wave equation from them.